Hello everyone, in today's video we are going to be looking at chapter 18 on kinematics. You may have noticed that your textbook has divided this chapter into two parts, one regarding differentiation while the other on integration. However, I've decided to actually merge these two parts together so that we can have a bigger picture about the idea of kinematics. So the objective of today's lesson will be to solve problems on displacement, velocity, as well as acceleration by differentiation as well as integration. Let us first take a look at the concept of displacement. The definition of displacement is that it is the change in position of the particle with respect to a fixed point at a particular instant. What this means in the pictorial diagram is that, let me get a pen out first. Okay, it means that if you're talking like a path, all right, on the straight line path, okay, so if I were to measure my distance from a certain fixed point, let's call this fixed point O. Okay, so the displacement itself, let's say if I were to be standing here, so imagine myself standing here, displacement is defined as this distance from where I'm standing to the fixed point O. Okay, so there is always this reference point whenever we measure displacement. Okay, so it has both magnitude and direction when it comes to displacement. So it matters where you exactly stand. So if I were to, let's say, stand over here, even though this value, let's say maybe if this were to be 2 meters and this were to be 2 meter, displacement wise, they are actually different because this is on the right of O, where over here, this is the left of O. So what we will usually say is that the right side is considered to be positive. So this displacement would be a positive 2 value, while this displacement here, this displacement here would be negative 2 in value. So it is summarized in this box over here, whereby if S, which is the symbol we use to represent displacement, if it were to be more than 0, the particle is at a point along the positive s-axis. The s-axis refers to this line that I drew earlier. Okay, so usually we take the right side as positive, okay, and left side as negative, similar to how we see right and left in our x-axis in our coordinate geometry topic. Okay, then for s less than 0, the particle is at a point along the negative s-axis. So we see that more than 0 and less than 0 are actually opposite in direction. And for s equals to 0, what it means is that it is at the fixed point itself. So at this point O, where I marked out earlier, okay, this is where the displacement is actually equals to 0. Okay, so I just want to summarize this. We see that the direction is given to us based on whether is it negative or positive, and the magnitude refers to the number itself. Okay, so in our example that I gave, the magnitude is actually the value 2. All right, I hope that this explains, this gives you a better idea about the concept of displacement. An additional point that I want to point out to you is that in our questions later on, you will find that very often there is this description. For example, distance from fixed point O. Okay, I will reiterate again when we come across questions later on. All right, so whenever we talk about distance from a fixed point O, it is the same as talking about displacement because we are talking with reference to a fixed point. So therefore, it is actually referring to the concept of displacement itself. Next, we take a look at the concept of velocity, where we use the symbol V to represent velocity. So it is defined as the rate of change of displacement. So it is about how much displacement actually change according to time. Okay, that is what rate actually means. So in other words, velocity can be the differentiation of displacement itself. Okay, there is a very long definition over here, but let me just summarize it where the focus is that velocity is the differentiation of displacement. So velocity itself also has direction and also has magnitude. It is a vector quantity itself for those that study physics. So when v is more than 0, meaning to say that the value is positive, it means that the particle is moving in the direction of the positive x-axis. That means that earlier on we took the right side to be positive. So let me maybe draw a pen here. So if I have a reference point O, if I had taken this right side as positive, okay, then velocity more than 0. So let's say if v is equals to maybe 50 meter per second, then this is actually referring to the fact that the particle, okay, is moving at 50 meter per second in this direction that I've just drawn out. Whereby if it were to be v equals to v less than 0, okay, it would be moving in this direction. So let's say v is equals to negative 50 meter per second. It means that it is moving to the left, which is the usual negative direction that we're referring to. So it is moving at a speed of 50 meter per second, but a velocity of negative 50. Okay, I don't want to dwell into the differences between a vector quantity and a scalar quantity because that's not our point of discussion here. It is for us to have some understanding about velocity. Okay, so when v is equals to negative 50, we just need to know that it is traveling in the opposite direction from the positive, and the value, the magnitude, okay, is 50. So magnitude in both examples that are given are 50. Then the positive and negative sign tells us the direction. Right? While if we say that v is equals to 0, it is actually that the particle is at an instantaneous rest. We use the idea of instantaneous rest for a reason. It means that it is temporarily at rest. It is at such a very quick timing, at a very short timing, that it is for an instant only. Okay, so usually when we say that it is an instantaneous rest, it means that there is this change in direction of motion. So when a particle, let's say if it starts over here, if it is traveling at a straight line like this, okay, when it wants to make a turn, okay, at this particular point where it makes a turn, there is an instantaneous rest. And this would mean that v is equals to 0. Okay, so we notice that at this section, okay, where it's traveling, your v is actually positive because it is moving in a positive direction towards the right, while at this part here, okay, you will find that your v would be less than 0 because it is moving to the left. Right? I hope that this gives you a better understanding about the concept of velocity. Next, we take a look at acceleration, whereby we use the symbol A to actually represent acceleration itself. Acceleration is defined as the rate of change of velocity. So what this means is that earlier on when we talk about velocity, okay, we said that it is actually the rate of change of displacement, which means the differentiation of our displacement function. While if we were to apply the same concept over here, our acceleration will be the differentiation of our velocity. Okay, so I want us to take a look at this part over here. Since our acceleration is the differentiation of velocity, and because our velocity is the differentiation of displacement, what this tells us is that acceleration will be the second derivative. That means we differentiate 2 times our displacement. Okay, we will be able to arrive at acceleration itself. Acceleration is again a vector quantity. So therefore, there is a magnitude as well as a direction. However, I don't want to go into the discussion about the positive and negative sign found in the acceleration itself because that is rather complicated. When we want to talk about direction, let us just stick to referring to the signs found in displacement and or otherwise your velocity. The sign found in your acceleration itself may not always tell you the direction. We need to rely on velocity to actually determine the direction of travel itself. Okay, so the deeper understanding about acceleration would have been discussed in your physics subject. Okay, we are not going to focus on the interpretation of the values in our maths subject itself. Okay, we are going to be focusing more on the calculation behind it rather than the interpretation of these values. So in summary over here, linking the ideas of displacement, velocity, and acceleration. Earlier on, we said that to get our velocity, we will do our differentiation from displacement. And to get our acceleration, we will do our differentiation from velocity. And to get acceleration, we could do 2 times of differentiation. That means the second derivative from displacement itself. Idea about how we can get velocity and acceleration by differentiation. Okay, since we understand that integration is a reverse process of differentiation, that means that we can apply our integration concept to get the other way. So I can get displacement from velocity and I can get velocity from acceleration. So with that idea, velocity will be the integration of acceleration and displacement will be the integration of velocity. Okay, so I hope that this very well summarizes for you how displacement, velocity, and acceleration is linked to our differentiation as well as integration. Let's now take a look at try 1 found in your textbook, page 147. So it says that a particle P moves in a straight line so that its distance s meters from a fixed point O is given by this. So to illustrate this idea, we usually draw a straight line path. So starting from O, okay, that's where your displacement is being measured. Wherever that it stops, let's say if it stops here, the displacement would be 12t minus 3t squared. Okay, our t values that we're using this in this question is from 0 to 4. We also want to take note how is time being measured. So time is actually taken in seconds after passing O. So at wherever that it starts, your time starts as well. Okay, so we might want to pay careful attention to how it is being described. Okay, especially later on when I show you a further example. So I'll talk more about it later on. In part I, we want to find the speed of P after 1 second. So let's first take a look at part I. So in the question part I, since we want to find speed and we are given the displacement function, we first do our differentiation. Okay, so differentiate with respect to t. 12t minus 3t squared, we will get 12 minus 6t. And since we're looking at after 1 second, that means that t is equals to 1. So we substitute in t equals to 1 into the velocity function, and that is 6. So therefore, the speed is 6 meters per second. Do take note that velocity and speed are slightly different. Speed is a scalar quantity, so there is no direction. So if let's say, if I found that my velocity value were to be negative 12 instead in value, our speed is actually 12 meters per second. But velocity is actually negative 12 meters per second because velocity has direction while speed has no direction. So this negative sign tells us direction. So in this particular case, since it's positive, velocity and speed actually are the same. Right, so I hope that answers part I for you. Moving on to part 2, which is found on the right side of this screen here. So we have to find the distance of P from O when the particle is instantaneously at rest. So distance of P from O actually refers to the displacement. So since we want to find out what is the displacement, I will definitely need to know what is the t value so that I can substitute the values respectively into this function over here. But in order for me to find the t value, okay, I need to make use of the fact that the particle is instantaneously at rest. So that means that v is equals to 0. So when v is equals to 0, I substitute it into my v function, which is 12 minus 6t equals to 0, and I solve that time is equals to 2. So when t is equals to 2, we find that the displacement, okay, we substitute into the function and displacement would be equals to 12. So the distance from O will be 12 meters. Do be very careful that we need to write in our units whenever we answer our questions as well. So in part 3, we want to find the total distance traveled during the first 3 seconds. So what you would probably do intuitively is that you will take t is equals to 3 and substitute it into this formula here, and we find that the value is equals to 9, and you think that this is the total distance. However, unfortunately, this is not the total distance, this is only the displacement. So let us first understand the differences between distance and displacement. So let's say if I were to be walking from home to school. So let me draw a diagram here. Okay, let me maybe use a green color here. So if let's say this is your home and then this is your school, and let's say the distance is maybe 5 km. And if you were to walk from home to school, your distance would be 5 kilometer traveled, and then your displacement will also be 5 kilometer because we are taking with reference to the home. Okay, so that would be not an issue. But if your journey is to be from home to school and back to home again, you will find that you travel 5 km to school and you travel another 5 km back home. So your total distance traveled is actually 10 km. I'm sure all of you would be able to know that. Okay. However, the displacement itself is actually 0 because from your current position, which is your home, okay, to the starting position, which is the reference point, which is also your home, you started from home and you ended up at home, your displacement is actually 0. Okay, so that is the differences between distance and displacement. All right, so now going back to this question in part 3, we understood in part 2 that there is this instantaneously at rest, okay, that was being mentioned. This was a very helpful thing because we know that when there is an instantaneous at rest, the particle actually makes a turn to the opposite direction. So if I were to illustrate it into a diagram, which I've already drawn one out over here, we started at O and then we went on in a straight line path, but when it is instantaneously at rest, which we have already found in part 2, that the time is equals to 2, we make a U-turn back, okay, towards our O. All right. So what this means is that my total distance is actually my travel from O itself right at the start to time is equals to 2, and then also including the distance that I have traveled from time equals to 2 to time equals to 3. So the total distance that I want to calculate is actually this red line that I have drawn. Okay, so what does this s equals to 9 actually means? How does it come into my diagram over here? Take note that displacement is always the distance from the reference point itself. So this 9 is actually when time is equals to 3, and when time is equals to 3, this is the location that we are at. Okay, and that distance from O, which I've already indicated with this green line, all right, this is actually my 9 meters. Okay, and earlier on in part 2, we found that when t is equals to 2, our displacement is equals to 12. So what this means is that when we put it into diagram, from the starting point O to time equals to 2, this green line arrow distance that I've marked out, okay, is actually 12 meters. But my distance, my total distance is not simply taking 12 plus 9, because we earlier on understood that our distance that we want is this red line that I have drawn. Okay, so I have this 12 meters, and then I need to add this up, this very short distance from t equals to 2 to t equals to 3. And this distance is actually my 12 meters minus away 9 meters. So therefore, I'm adding the 12 meters here from time equals to 0 to time equals to 2, and to add it to 12 minus 9, which is my distance traveled from time equals to 2 to time equals to 3. So the total distance that has been traveled is actually 15 meters. All right. Okay. I just want to maybe make a casual note on the side that this diagram, okay, is just for illustration purposes. I'm not trying to find a curvature kind of distance. I'm not trying to find a curved length at all. So please do not use any strange formulas. I'm just really drawing it along a straight line path. So imagine yourself walking along a corridor and you walk in the straight line path, and then you just turn back only without having to take a step, okay, to your left or the right to make a U-turn. Okay, so I hope that you understand what I have been trying to cover in try 1. Now let's move on to try 2, whereby in this question it says that a particle moves in a straight line so that at time t seconds after leaving a fixed point O, its displacement s meters is given by this function s equals to 2 sine 3t. So it is not your usual conventional algebraic expression. Okay, we are having a sine function over here. So in part I, we want to find the value of t when the particle first returns to O. So the fact is that the time is actually measured when t is when it is at O. So let me draw the pen first. Okay, so time is measured from O itself. So time is equals to 0 over here. And your displacement is also being measured with reference to O itself. Okay, so if you want to find the value of t when the particle first returns to O, it means that maybe it has traveled somewhere over here like that before, and then after it reaches back at O. So the displacement here would actually be s equals to 0. Okay, so with the idea in mind, let's go into solving this question. So in my answer over here, s equals to 2 sine 3t, we use s is equals to 0 to substitute into this equation, and then we solve, okay, this our trigonometric function. So sine 3t is equals to 0. How I go about solving it is to rely on our sine graph. So what I have over here on the right is the sine graph. Okay, so it is a graph of y equals to sine 3x, whereby instead of x-axis, I have my 3x over here. So there's nothing special at all actually. What I actually am using the graph for is to actually plot out the essential points, which is the entire period to be 2 pi, and then having half of it to be pi, another half is pi over 2, and 3/4 of it is at 3 pi over 2. So since we want sine 3t equals to 0, that means the y-axis is actually equals to 0. Therefore, I've marked it out with the green crosses. These are the points where y is equals to 0. And that means that my time, or my 3t, okay, is actually 0, pi, and 2 pi. So that's how I get 0, pi, and 2 pi over here. Okay, so this falls back onto your trigo equation solving skills. So time is equals to 0, pi over 3, or 2 pi over 3, because you divide throughout by 3. Okay, and then particle first returns to O when time is equals to pi over 3. Because we are looking for the first time it returns to O, it can't be t equals to 0, because t equals to 0 is simply representing how it actually started at O itself. Okay, and since we want the first time it actually returns to O, it is actually pi over 3. So therefore that's the answer. I want you to also notice that in my calculations, I have been using radians for my time value. It doesn't make sense at all, okay, for us to use these numbers to be in degree, because time can't be in degree. Time is measured in seconds, minutes, hours, and all that, okay, but it can't be measured in degree. Okay, so the value radian itself is actually, radian is actually not a unit at all. Okay, so it's just a measurement. Okay, so you can recognize it as a number, a value itself. Okay, that has no unit. Therefore, whenever we do our kinematics, okay, our topic of kinematics involving any form of differentiation or integration or any solving, the angle itself would typically always be used in radians. And now moving on to part 2, it says that the particle first comes to instantaneous rest at the point A So we want to find the value of t at A. So instantaneous rest would mean that your v is equals to 0. So what we have to do is to figure out the velocity function first. So since s is equals to 2 sine 3t, we do our differentiation. So, in doing our differentiation, the 2 we keep it. For sine itself, when we differentiate, becomes a cosine. The angle remains the same. And then this 3 over here needs to be taken out according to our chain rule. Okay, so that means our velocity function is equals to 6 cosine 3t. So when v is equals to 0, because we're looking at instantaneous rest, 6 cosine 3t is equals to 0, and we solve that cosine 3t is equals to 0. So using the same method of using the graph, this is my cosine graph. The period of a cosine function is 2 pi. Okay, and then half of it is pi, another half is pi over 2, 3/4 of it is 3 pi over 2. So when the value here is 0, so when y is equals to 0, it is where the green crosses are. That means your time is equals to pi over 2 or 3 pi over 2, or in more particularly, it's 3t that is pi over 2 or 3 pi over 2. So therefore, t is equals to pi over 6 or 3 pi over 6. Since we want to actually find out the first time it comes to instantaneous rest, that means that t is equals to pi over 6 only. Then in part 3, we have that we want to find the acceleration of the particle at A. So again, acceleration is the differentiation of your velocity. So we need to differentiate our velocity over here. So the differentiation of the cosine function is a negative sign. So do remember that. Okay, and then we also need to take out the 3 according to our chain rule. So it simplifies to negative 18 sine 3t. Okay, since we want to find the acceleration of the particle at A itself, and the time at A is actually what we found in part 2, which is pi over 6. So we substitute in pi over 6 into our acceleration function, and we find that our acceleration will be negative 18 meter per second square. Okay, the function A itself finds for us the acceleration, so there's no need for us to go and interpret whether is it a deceleration or acceleration. We just take it as A as acceleration, therefore answer will be negative 18 meter per second square. Okay, that's the unit for acceleration. Now let's challenge ourselves further by making sure that we can understand and interpret the question correctly. So let's take a look at exercise 18.1, question 6, which is found in your textbook, page 150. Let's read the question together first. Okay, it says that a particle P moves in a straight line, so that its displacement s meters from a fixed point O on the line is given by s equals to 2t squared minus 18, where t seconds is the time after passing a point B on the line. Okay, I want you to take note these parts that I've highlighted over here. Notice that the displacement is measured from a fixed point O, but the time is actually measured after passing a point B. So there is some differences in terms of how it's starting in this case. Let's try to put that into diagram. Okay, so in displacement, let's say I have a straight line path over here and I have a point O. My displacement is such that if I were to be standing, let's say over here, okay, then my displacement is going to be measured in this manner. And how I calculate it is that I have a formula to calculate. Okay, even if I were to be standing here, my displacement can also be calculated using the formula, so long as I know the time value. Okay, I need to know what is the time here in order for me to find out what is the displacement. Okay, but the problem here is that your time is actually taken after passing a point B. So time is taken at, let's say, if my B were to be over here. So at this point, this is where it starts, t equals to 0. What this means is that, okay, the particle, which is the thing that we're talking about in this question, okay, it is not starting off at O, okay, it is actually starting off at B. Okay, so it is as though, let's say if O is the starting line, okay, the person did not start at the starting line. That person actually stood at maybe 2 meters away from O itself, okay, maybe behind O. I'm just giving a very big example over here. B may not actually be on the left, it could also be on the right of O. Okay, so we do not need to do any recalibration or readjustment. We just need to pay very careful attention to these details in the question. Right? So I hope that this gives you some idea about the information given in this paragraph. Now let's proceed to part I, okay, so that we can draw a clearer picture of this entire question. Okay, so part I, we want to find the initial displacement of P. That means that we want to know where is this P at, okay, when time is equals to 0, because we're talking about initial. So very simply, when time is equals to 0, I have a function for my displacement already. I substitute time equals to 0 into that, and I find that S is equals to negative 18. So what this means is that if I have a reference point O, my initial point when t equals to 0, okay, which is my point B, is actually 18 meters to the left of O, because, oops, I'm sorry, okay, because we know that it is negative 18, so it must be on the left of O. So the initial displacement will be negative 18 meters. Okay, take note that it's displacement that we're talking about here, so there must be the negative sign since that's calculated from our S function. Okay, moving on to part 2, we want to find the velocity of P when it passes O. Since we have the displacement function, we do our differentiation to find out the function for V. So differentiate over here. And in the question, we want to find out when it passes O. Okay, so passing through O. So let me just draw the diagram that we had earlier just now. O is here, B is here. Okay, we do not know what is the time that it passes through O. But we know at the very least is that if I were to stand here, okay, already, my displacement will be equals to 0. So when S equals to 0, okay, I substitute into my displacement function, and I solve that my t value will be 3 or negative 3. So this means that only 3 seconds later, then I will be at the position O. Okay, since we're trying to find velocity, we're not trying to find time yet. Okay, so we substitute in time equals to 3 into our velocity function, and then we get velocity to be 12. So therefore, the velocity when P passes O will be 12 meters per second. Okay, I rejected this negative 3 because time cannot be negative. Right? I hope you understand how I proceeded into solving this question. Moving on to part 3, we want to show that P never comes to rest. The key word here is never. Okay, and also the idea of rest. When it comes to rest, surely we are no longer moving. If you're not moving, your velocity should be equals to 0. Okay, we want to show that P never comes to rest. That means that your velocity cannot equals to 0. Okay, so in part 2, we already know what is our velocity function, which is v equals to 4t. We understand that time will always be more than 0. Okay, so since time is always more than 0, your 4t must always be more than 0. Okay, so when 4t is always more than 0, that means your velocity is always more than 0. Hence, P actually never comes to rest. because velocity being more than 0 means that it's always moving. Okay, so therefore I've proven that P never comes to rest. Let's move on to part 4. We want to find the average speed of P in the first 4 seconds. So average speed actually refers to total distance over total time. Again, I want to emphasize on this fact that it is total distance because speed is a scalar quantity. Speed is distance over time. Okay, it is not displacement over time. Displacement over time actually refers to velocity, or rather average velocity equals to total displacement over total time. Okay, so let's get back to what we have gathered so far in terms of information. We know that there's a reference point O that helps us to measure our displacement, and then there is a starting point B, that is where t is equals to 0. We have the particle P moving in a straight line to the right because we take right as positive, and we have seen that V is always more than 0. So therefore, it's always going in a straight line path. It never comes to a stop. Okay, and our question wants us to find the average speed in the first 4 seconds. So therefore, t is equals to 4. So what I need to find is the total distance here. So when t is equals to 4, we find that the displacement s is equals to 14 meters. Okay, however, do take note that s equals to 14 is not the total distance in the first 4 seconds, because s is a displacement measured from O. Alright, so to illustrate this into our diagram, this 14 meters is actually this part here only. Okay, so earlier on in our part I, we know that our B is actually 18 meters away from O, or rather S was actually negative 18. Okay, so the total distance is actually 18 meters. We can ignore the negative sign because that only simply tells us the position with reference to O. So the total distance is 18 meters plus 14 meters. So therefore, I need to do this calculation to find the total distance to be 32 meters. And in conclusion, our average speed will be 32 meters over 4, and that is 8 meters per second. Okay, and that sums up our question 6. We will now take a look at try 3 that's found in your textbook from page 152 to 153. So let's read the question. It says that a particle moving in a straight line passes through a fixed point O with a velocity of negative 4 meters per second. So when it passes through the fixed point O, that is where time also is taken to be after passing through O. So when t is equals to 0, so let me draw it out. So we have a point O. When t equals to 0, we find that the particle actually moves with a velocity of negative 4 meters per second. Okay, and then there is this acceleration, which is given by 6t minus 11. Oops. Okay, in part I, we want to find an expression, okay, for the velocity of the particle in terms of t. So earlier on, right at the beginning, I shared that velocity is the integration for acceleration, because we know that integration and differentiation are just opposite of each other. So therefore, to find the velocity, I will do my integration. Do take note that my integration is actually indefinite integral. So therefore, there is a plus c. Do be very careful about that. Okay, so my answer will be v equals to 3t squared minus 11t plus c. but it is not yet complete. I need to find out what is the value of c. How am I supposed to find that? Okay, recall that right at the start of the question, we mentioned that when t equals to 0, the velocity is actually negative 4 meter per second already. So we substitute in this information into our expression for v. So negative 4 is equals to 3 0 square minus 11 0 plus c. So I will see that c is equals to negative 4, and therefore v is equals to 3t squared minus 11t minus 4. Okay. Moving on to part 2, we want to find the displacement of the particle when t is equals to 4. I only have the acceleration and the velocity function currently. I do not have the displacement function. So displacement is the integration of our velocity. So again, we need to integrate. Okay, and don't forget our constant over here because we're doing we're doing an indefinite integral. You can use plus c. I just decided to use plus d. Okay, as long as it's a constant, it's fine. So long as you don't use letters like e or o. Okay, so likewise, I need to find out the value of d. And what we understood from the information here is that when time is equals to 0, the displacement is equals to 0 because it's all with reference to the point O. Okay, substituting this idea into my expression above, I will find that d is equals to 0. Okay, because all these parts here becomes 0 upon substitution. Okay, so therefore s is equals to t cubed minus 11 over 2 t squared minus 4t. Now, going back to the question, we want to find the displacement when t is equals to 4. Substitute t equals to 4, and then we find that displacement is negative 40, which is the answer. Okay, so displacement equals to negative 40 meters. Moving on to part 3, we want to describe the particle's motion when t is equals to 4. So we need to mention about how the particle is actually moving when t is equals to 4. Okay, we cannot assume that the particle is always going in a straight line. Okay, it could always be turning and all that. So we need to go and find out, okay, whether there's any turns or not. So whenever there is a turn, that means that it will come to an instantaneous rest. So that means that v is equals to 0. So using my answer that I found from part I, okay, substitute in v equals to 0 into it, and I will be solving the question, or rather the equation, by doing factorization. Okay, and I will see that t is equals to negative 1/3 or t equals to 4. It's not possible for time to be negative, so there is only a turn, okay, at t is equals to 4. Okay, then when t is equals to 4, the particle comes, that means that in doing our description, the particle comes to an instantaneous rest and turns to the opposite direction when time is equals to 4. You may be wondering, why is it that I don't just take when t is equals to 4, I find out what is the velocity. Okay, essentially my velocity will be equals to 0. And then you will start be able to conclude that when v is equals to 0, particle comes to instantaneous rest and then it will turn. Okay, however, we want to just make sure that from time equals to 0 to time equals to 4, this is the only turn that it makes. Okay, because in between, what if there are many other turns as well? Okay, then we wouldn't know whether is it still going in the opposite direction or is it going in the same direction as the particle at the beginning. All right, so therefore this is the process that we decided to go through to make sure that we find out all the time periods, okay, where there is a possible turn. Okay, hence this wraps up our try 3. Okay, let's move on to try 4. In try 4, what we have is that a particle travels in a straight line, so that t seconds after passing a fixed point O, the velocity is given by this function. We want to find an expression in terms of t for the displacement of the particle from O at time t. So displacement is the integration of velocity. That's what we're going to do first. Okay, we do our integration, not forgetting the plus c constant. And then we need to find out the plus c. Okay, so how did I get this information here? Okay, question says that t seconds after passing a fixed point O. That means that when time is equals to 0, your displacement is also equals to 0. Because all your displacement, okay, is measured from O itself. So therefore, I put it into my expression, then I will see that c is equals to 0. Do be very careful that c is not always 0 all the time. So therefore, the displacement is being represented with this function. Moving on to part 2, it wants us to find the value of t when the particle is at instantaneous rest. That will mean that v is equals to 0. Substitute that into our velocity equation, factorize, and we find that t is equals to -5 or t equals to 2. Needless to say, we reject the negative time. So it is an instantaneous rest only when time is equals to 2. Moving on to part 3, we want to find the distance traveled in the second. Okay, seems like a tongue twister here. I want us to pay attention to this phrasing. It says that in the second. Okay, what does the second actually mean? Okay, so looking at this diagram that I've drawn a straight line, like a timeline. So when t is equals to 0, that is right at the beginning. Then we have t equals to 1, then we have t equals to 2. From t equals to 0 to t equals to 1, that is what we call the first second. And then from t equals to 1 to t equals to 2, that is what we call the second. We only want the distance traveled in the second. That means it is the distance traveled from time equals to 1 to time equals to 2. Okay, sorry, my cursor isn't quite following, it's a bit laggy. Alright, so I hope you understand what is it that we're trying to find now. Okay, so when we have our displacement function here, intuitively you will find t equals to 2 and substitute into it. And then you will see that s is equals to -11 and 1/3. However, this is not the displacement, okay, in the second, because if I were to draw out the actual situation here, O is the starting point. Okay, when t equals to 2, my displacement is 11 and 1/3 meter, or rather -11 and 1/3 meter. So that means it is to the left of O. Okay, and this distance itself is 11 and 1/3. But I only want the distance that it traveled from time equals to 1 to time equals to 2. 11 and 1/3 is actually time equals to 0 to time equals to 2. That's assuming that there's no turning point. Okay, that it moves in a straight line path. But what we want to find in this question is the distance traveled from time equals to 1 to time equals to 2. So what we need to find is this displacement from time equals to 0 to time equals to 1. Okay, and that is 8 and 1/6, because when I substitute in t equals to 1 into my displacement equation, I find that my s is equals to -8 and 1/6. That means it is actually located to the left of O, and that is 8 and 1/6 meters in distance. So now I can see that the distance traveled, okay, in the second will be 11 and 1/3 meters minus away 8 and 1/6 meter. So that will be this distance that we want to find here. Okay, and that is 3 and 1 over 6 meters. And now we look at the last part, part 4, where we want to find the total distance traveled in the first 3 seconds after passing through O. So recall that in part 2, we mentioned that the particle actually comes to instantaneous rest when t equals to 2. So there is this turn that's going to be made at t equals to 2. Then we arrive at t equals to 3. Okay, so the distance traveled that we want to find is actually this one that I'm pointing with my laser over here. Okay, so earlier on in my part 3, I have already found the displacement from O to time equals to 2, which is 11 and 1/3 meters. Okay, so what I'm short of is this distance over here. Okay, however, I can only find that if I know the displacement when t equals to 3. So I substitute t equals to 3 into the displacement function that I have, right? And then that will be negative 7.5 meters. So therefore, in my diagram, what this means is that 7.5 meters is actually this distance over here. So the total distance traveled will be 11 and 1/3 meters plus 11 and 1/3 minus away 7.5, so that I can arrive at this distance here. Therefore, my answer will be 15 and 1 over 6 meters. We now take a look at try 5 that's found in your textbook page 155. Okay, so this question says that a particle moves in a straight line so that at time t seconds after leaving a fixed point O, its velocity is given by this equation. We want to find its initial acceleration as well as the displacement from O when t equals to 4. So to find acceleration, I need to differentiate my velocity function. So I do my differentiation. Okay, so for the exponential function, when you differentiate, it remains the same, but not forgetting that there is a coefficient of t, which is negative half. Okay, therefore I have this negative half here. Okay, that is your chain rule application. So acceleration is given by negative 40 e to the power of negative half t. So initial acceleration is what we want to find. Therefore, t is equals to 0. And substituting it into here, I will find that we have negative 40 e to the power 0. Be very careful, e to the power 0 is equals to 1. Okay, it's not equals to 0. It's a very common careless mistake. Hence, the initial acceleration will be negative 40 meter per second squared. Moving on to part 2, where we want to find the displacement from O when t is equals to 4. So we need to know the displacement. So I do my integration of my velocity function. So I integrate over here. Okay, so when integrating an exponential function, it remains the same. However, again, we have the coefficient of t, which is negative half, which we need to divide here. So that simplifies to be negative 160 e to the power of negative half t, and very importantly, the plus c. So when time is equals to 0, displacement is equals to 0 due to this statement here. Okay, therefore I can find that my c value will be equals to 160. Again, e to the power 0 is 1. Okay, so therefore c is 160, and I now have a complete function for the displacement. Okay, question just wants to find the displacement from O when t equals to 4. We just have to take t equals to 4 and substitute it into the displacement equation. Press that into our calculator, leaving our answer to 3SF, and I will have 138 meters as our answer. We have come to our very last question for this chapter. So let's take a look at try 6. Okay, that's in your textbook page 156. There's a lot of information for us to comprehend in this question. So let's take a look. It says that there are two particles P and Q leaving a point O. So as I read the question, I will illustrate it into a diagram here so that I can have to-go diagram to consolidate all the information that I have. So starting at point O, that is your time equals to 0, P and Q. And then it moves in the same direction along the straight line. So therefore I drew arrows like that. P starts with a velocity of 7 meters per second. So that means that when T is equals to 0, okay, V is equals to 7, and it moves with a constant acceleration of 1 meter per second squared. So therefore, I have V equals to 7 and A equals to 1 over here. This is when T is equals to 0. Then for the particle Q, it starts from rest. That means that V is equals to 0. Okay, and then it moves with an acceleration of A meter per second square, whereby A is actually this expression of 1 over 5 times 2 plus 3t. Okay, and t seconds is the time since leaving O. We want to find expressions for the velocity as well as the distance for part I and part 2. So let's go into doing part I and part 2 first. Okay, I have the diagram that I drew consolidated over here. So let's look at for the particle P, okay, in part I. Okay, for particle P, we want to have a generic velocity expression. This V equals to 7 is only at the time when T is equals to 0. It is not trying to say that the velocity is always the same. However, the A equals to 1, okay, is a useful information because the question says that it moves with a constant acceleration. This tells us that forever, okay, so long as P is moving, the acceleration remains constant, meaning to say that the acceleration remains the same all the time. Okay, acceleration remains the same all the time. Right, so that's a crucial information. That means that A equals to 1 is what the acceleration is going to be all the time. Okay, so velocity being the integration of your acceleration, we do our integration, and then we have V equals to T plus C. Now, I need to find out what is the C, and we know that when time equals to 0, velocity is equals to 7. Okay, so C will be equals to 7. So therefore, the velocity for the particle P is represented by T plus 7. Okay. Then for particle Q, we do the same as well. Okay, question says that Q starts from rest and moves with an acceleration of A meter per second square. So that means that the acceleration is always again the same throughout for all the time because A is equals to 1 over 5, 2 plus 3t. It is being modeled by this expression here. So we can always substitute in time values into this, and I will be able to know what is the acceleration at that particular time. So I need to expand it first in order for me to do integration. Okay, so over here, I'm actually integrating, or I have already integrated it. Okay, I just skip that step because I'm lacking space in this single page that I have. Hence, V is equals to this and plus C, not forgetting that. We know from the question that T equals to 0, V is equals to 0 because question says that it starts from rest. Okay, so we see that C is equals to 0, and therefore the velocity for particle Q can be represented by this expression. Okay, moving on to part 2 where we want to find the distance. So let's break it up in two parts. So for particle P, we know that velocity is T plus 7 already from part I. We do our integration, not forgetting the plus C again. And when time is equals to 0, we know that the displacement is 0 because the particles all started at the reference point, which is O. So C will be equals to 0 upon calculation. So the displacement for particle P would be following this expression. We do the same thing for particle Q. So velocity was what we found in part I. We integrate. Okay, not forgetting to find the value of C. We know that when t equals to 0, s is equals to 0 as well, because both particles started at the reference point O. So c is equals to 0, and therefore the displacement q would follow this expression here. So now we have the velocity and the displacement expressions already. We will now move into part 3 and part 4. So in part 3, it says to find the distance from O when P and Q collide. Okay, so we need to understand what does colliding means. Okay, so colliding means that they are actually at the same same location itself, because they must meet in order to collide. Okay, so how does this collision actually work? Okay, so just now we had our O, and then we have P and Q, right? Okay, they both travel at different speeds, by the way. So Q could be faster than P, or P could be faster than Q. I'm not too sure. I didn't dwell into looking at the velocity expression that we have. Okay, so essentially, although one is faster than the other, maybe at some point it started to slow down, I'm not sure, okay, such that they managed to catch up. Okay, and then they meet at a certain point again. And this is what we mean by collision. Okay, so therefore the displacement will have to be equal. The displacement from O will have to be equal. So SP equals to SQ. So we make use of the displacement expression that we found in part 2. Okay, and we equate it together such that we have this. I don't like to work with fractions, so I multiply on both sides by 10. Oops. Okay, so that I deal with integers and I simplify it, and I see that I have something cubic. This is something manageable for us to solve because there is no constant term. Okay, so everything has a common factor of t. So what I took was that I factorized out the common factor of t. Then I'm left with something quadratic. This quadratic one can be factorized. Okay, so my time values will be t equals to 0, t equals to 10, or t equals to -7. Time can't be negative, so therefore I rejected this. Time equals to 0 is when they started. They started both at the same point. That is not counted as our collision. So this one we reject also. So therefore, the time that it collided was actually t equals to 10. Not forgetting that question actually wants us to find the distance. The question is not asking us to find the time. So in fact, it is the distance from O, which is essentially displacement itself. So I just substitute in t equals to 10 into either one of the displacement equation. Okay, so what I did was to substitute into the displacement equation of P, and I will see that the distance from O will be 120 meters. And that's how we solve part 3. Let's now take a look at part 4. So we want to find the speed of each particle when they collide. We already found in part 3 that they collided when t is equals to 10. Okay, so there's no need for us to do the same few steps again. So when time is equals to 10, we substitute into our velocity expression that we found in part I, and the particle, the speed of particle P is 17 meter per second, and the speed for particle Q is 34 meter per second. Okay, so that wraps up our try 6. And that is all for our chapter 18. Please check on your Google Classroom for any homework assignment. Alright, I'll see you in the next video.